Apart from the technique of using two networks, there's another important technique, experience replay. We need to answer two questions. First, what is experience replay? Second, why do we need to use experience replay? Let's start with what experience replay is. When we collect experience samples, there is always a sequential order of them. However, when we use these samples, we don't necessarily have to use them in the order they were collected. It's not first come, first use. How do we use them? We put all the samples into a set which is denoted by B. Each element inside this set is an experience sample. We are in state S, take action A, receive a reward R, and transition to the next state S prime. This set has a name, replay buffer. When I need to train the neural network, I mix all the samples and randomly select some samples from this set to train the neural network. This process of selecting and reusing samples is called experience replay. That is because the experiences are already stored, and we are replaying them by using them again. When selecting these samples, it's important that the selection follows a uniform distribution, meaning that every data point in the set should have an equal probability of being selected. Why is experience replay necessary? Why is it necessary to follow a uniform distribution? Let's answer these questions. The answer actually lies in the objective function. In this objective function, there are several random variables, R, S prime, S, and A. To calculate the expectation of these random variables, we need their probability distribution. First, let's consider the distribution of S and A. Here we treat SA as an index and consider it as a single random variable. What does this mean? For example, if I have n states and each state has 5 actions, then I have a total of 5n actions. How do I index each action? I can use SA as an index which corresponds to a specific state and action, similar to a point on a 2D plane that has x and y coordinates. So, SA forms a random variable that must follow a distribution denoted as D. We'll discuss what this distribution is shortly. Now let's look at the other two random variables, R and S prime. Once S and A are given, R and S prime follow the system's model, which doesn't require much discussion. So, let's return to the distribution of SA. We assume here that its distribution is uniform. Some readers may ask, why must it be a uniform distribution? Can't other distributions work, like a Gaussian distribution? The problem here is that we do not know the true distribution of SA. In this case, the best option is to treat them equally, meaning every SA pair has the same probability, which leads to a uniform distribution. Now, here's the problem. I assume that SA obeys a uniform distribution, but when I collect samples, it's collected according to other probability distributions. So, what do? It's actually quite simple. I just don't use the samples in the order they were collected. Instead, I use experience replay. I put all the samples together and then sample uniformly from them. This breaks the correlation between the samples. This explains why experience replay is necessary and why we need to sample uniformly. We've just introduced the technique of experience replay. Now let's revisit what we learned about tabular Q learning. I am going to ask a few questions now. If you can answer these questions well, it means you have a good understanding of Q learning, both in its tabular form and its function-based form. The first question is, in tabular Q learning, we don't have experience replay. This is obvious, we didn't mention it before. But why? Why didn't we need experience replay before, yet we do in deep Q learning? The answer is simple. Previously, we didn't deal with the distribution of the state action pairs SA. If they must obey a specific distribution, such as a uniform distribution, then you need to put them together and sample them uniformly. If there's no such distribution requirement, there's no need to do that. Another question follows. Why does deep Q learning involve the distribution of SA, but tabular Q learning does not? The answer lies in the difference between tabular and value function methods. Deep Q learning is a value function method. It aims to optimize a scalar objective function. This scalar objective function is an expectation that involves the distribution of SA. On the other hand, when using tabular Q learning, this distribution isn't relevant. Why? Because tabular Q learning is to solve the Bellman optimality equation. That is to optimize the state value for every state. Another question. Although experience replay isn't necessary for tabular Q learning, can it still be used? The answer is yes. Even with tabular Q learning, you can use experience replay. Why? Because tabular Q learning is an off-policy algorithm. Off-policy means that it doesn't matter how the samples were obtained. Whether the samples were collected sequentially or in other ways doesn't matter. As long as you give me a SA pair, I can update the corresponding Q value for that SA pair. Moreover, there are some advantages to using experience replay. What are these advantages? One key advantage is that it makes your sample usage more efficient. Why? Because you can reuse the same sample multiple times. Specifically, since you're sampling uniformly from a replay buffer, there's a chance you sample the same experience multiple times. This allows you to better use each sample. Previously, with tabular Q learning, there was some data waste. You may not remember, but we had a simulation example where Q learning used episodes of 100,000 steps. In fact, we don't need that many steps. What we need is that every state action pair is visited at least once. Whether you visit it many times or just once doesn't make much difference, especially in a deterministic environment. Of course, if it's a stochastic environment, that's a different story. As long as each state action pair is visited once, that's enough, and you can reuse the experience samples repeatedly. Previously, because we followed the sequence of samples, once an experience was used, it was discarded, which led to a waste of data. That wraps up these questions. I believe they are somewhat tricky, but I hope you understand them. Once you do, your understanding of the TD algorithm and value function methods will be much deeper.